So I'm very pleased to announce to have Sönke Dangendorf give a presentation to us today on sea level change issues. Sönke received his undergraduate in civil engineering and graduate degrees from University of Siegen in Northwest Germany. And he worked as a staff scientist and assistant professor there also, and is currently an assistant professor at Old Dominion University in the Department of Ocean, Earth and Atmospheric Sciences. And he will be moving to Tulane in January, to take up an assistant professorship there in the Department for River, Coastal Science and Engineering. So maybe we can, you can share your screen, Sönke, and I became aware of Sönke's work when I was working on a proposal for Nash Academy of Sciences, and he has written incredible papers in very prestigious journals in Nature and PNAS and others, and his work was extremely helpful to us as we were putting together the proposal. And I hope we may have opportunities to collaborate in the future when he moves to Louisiana. Thank you, Sönke.
Yeah, thanks a lot, Bridget, for that very kind introduction. And thank you all also for that kind invitation. Yeah, today I want to talk a little bit about some ongoing work on probabilistic reconstructions of global and regional sea level rise, as well as individual contributors over the 20th century. So as the title suggests, I'm talking about reconstructing fields of sea level change over the entire ocean that go back to 1900. Some of the results that I'm presenting today are pretty new, not peer-reviewed, so some is definitely work in progress. So, but let's start at the beginning with some basics. Nowadays, since 1992, we are able to measure sea level changes from space. Since 1992, satellites measure sea surface height with a very high precision and near global coverage from space. The record, the global mean record of these measurements is shown in this plot from NOAA. Below, it's the blue curve. And it clearly shows that ocean sea levels are rising over that period by an average rate of 3.3 millimeters per year. It is now also very well known that the rate of change is increasing as well. So the record shows an acceleration, a positive acceleration, meaning that the rates are rising faster and faster. In addition to these satellite measurements of sea level itself, we nowadays, since 2003 and 2005, also have complementary measurements of the individual contributions or the two major causes of sea level change. There are two causes. One is, of course, we can either add or remove mass to the ocean. For instance, now the Earth is warming. We all know that. So ice sheets and glaciers are melting and adding mass to the ocean. That's what we call barystatic mass changes. Of course, the ocean is also warming, and if the ocean is warming, it needs more space, so it expands. And that component for the global mean, we call that thermal expansion. So both of these two components are measured by two independent measurement systems. Both are shown in this plot below as well. In red, we see the global mean thermal expansion as measured by Argo floats. Argo floats are floats moving through the ocean and measuring temperature, salinity, and pressure to get density changes on a global scale. And we see that the ocean has been warming, and due to the warming, it has been increasing by approximately 1.3 millimeter per year since 2005, so roughly 1/3 to the total sea level change. We also have another satellite system, the gray system that measures changes in ocean mass and barystatic ocean mass on a global scale. These are two satellites that surround the Earth and measure any changes in mass on land or in the ocean. These can be used to estimate the contributions by land ice, for instance, Greenland, Antarctica, glaciers, but also from any terrestrial sources of water storage, for instance, water behind dams or due to hydrological changes. The resulting global mean is shown here in green. It has been increasing by 2.1 millimeters per year since 2003. The increase is primarily related to glacier melting and the melting of the two large ice sheets, in particular Greenland. The little wiggles that you see, the variability, that is primarily induced by hydrological changes or changes in the hydrological cycle. So we can take these two independent measurement systems, put them together and compare them to the satellite measurements. That's what we call the sea level budget, having independent contributions, putting them together and comparing them to the total. This is the yellow curve in this plot, and you can see that it agrees very well with the satellite measurements, meaning that we can close the sea level budget and understand the different contributors since about 2005 very well. Satellite measurements also provide us information about sea level changes over the entire oceans, so about regional sea level. And this map is actually based on satellite altimetry data provided by CSIRO in Australia. And it shows the linear trends from 1993 to 2018 after the removal of the global mean. So it's really just the regional variation. And we see that there's a lot of variation going on. So these rates range from approximately from -5 to +5 millimeters per year at individual locations. And there are different reasons for that. First of all, we have to keep in mind that when ice melts and an ice sheet or a glacier loses mass and contributes that to the ocean, it's not only that static bathtub effect that is going on, but there are additional processes that are initiated. An ice sheet in the current situation is, of course, a very heavy body of mass. It is such a heavy body of mass that it attracts gravitationally the ocean around it. So in the moment, we see actually high sea levels surrounding the ice sheets or glacier regions in the oceans. But when these ice sheets or glaciers lose mass, there are two additional processes that are initiated. First of all, due to the loss of mass, the sea level, or the gravitational pull is reduced as well. So this leads to a fall of sea level near the ice sheet and a rise of sea level in the far field from approximately 2,000 kilometers far away and beyond. At the same time, of course, this heavy body of mass also suppresses the ocean floor on which it is grounded. So when this melts, that ocean or that ground beneath will uplift as well. So these are two additional processes in addition to the barystatic sea level change that we see in the global mean. And I marked these two areas in Greenland and in Alaska. These are typical regions. We see their negative sea level trend. This is actually a fingerprint of these of the recent mass loss in these regions. Another process that explains this large spatial variability in sea level is related to so-called stereodynamic effects. This is ocean mass redistribution induced by winds or ocean circulation systems. One example here are the large positive rates in the Western Pacific and the large negative rates in the Eastern Pacific over that period. Over that period between 1993 and 2018, we had an accumulation of a lot of La Nina winds, which led to an increase in the Pacific trade winds, pushing the water masses from the eastern side to the western side, explaining that gradient in sea level. So we can also plot the location of tide gauges into that map of spatial sea level changes. Tide gauges are actually the only measurements of sea level that we have before the satellite era, starting in 1993. Tide gauges are local devices that are grounded on land and measures sea level relative to the land. In this plot here, you can see the same trend map as before, but the little dots show the same regional sea level trend as measured by tide gauges at the specific locations. In principle, you can see that over the larger scale, the two estimates agree relatively well. So in blue areas, you see usually also blue patches from the tide gauges. But you can imagine, because of the location of the tide gauges, they are primarily located along the coast with a very strong hemispheric bias towards the northern hemisphere, and primarily along the coast with only very few tide gauges located on islands in the open ocean. And you can imagine, just by that location, even in the ideal situation of today, where we have more than 1,000 tide gauges, it will be very, very difficult to actually estimate a true global mean from that network, because we miss large parts of the ocean. And that situation becomes much more complex when we go back in time, because back in time, beginning of the 20th century, we only have about 80 or 90 tide gauges that measure sea level, most of them located in North America and Northern Europe. So this is a very complex task. If we actually look at the rates of sea level change from tide gauges in comparison to nearby satellite altimetry in more detail, we actually see that there are several spots or several dots that are significantly different from the maps that we get from satellite altimetry nearby. And this is related to the fact that tide gauges measure sea level in a very different way than satellite altimetry does. Satellite altimetry measures sea level to the Earth relative to the Earth center of mass. So it really just measures the pure motion of the water in the ocean, but nothing related to the solid Earth. Tide gauges instead measure sea level relative to the land on which they are grounded. And that means they not only measure that pure sea level signal, but also the vertical motion of the ground beneath. So this vertical land motion can occur due to two different processes in principle, or groups of processes. There's a natural process that we call Glacial Isostatic Adjustment, or GIA. This is actually the response of the Earth to the ice coverage during the last ice age that ended 23,000 years ago. And if we look in that box over Scandinavia in the middle of the map, this is actually a region that was covered by ice. And due to the loss of ice after that ice age, the land is still moving up. And it is moving up in an order of up to 8 or 9 millimeters per year, which means that sea level in northern Scandinavia are generally falling, despite the warming of the oceans and the increasing mass loss. Another example can be anthropogenic vertical land motion. For instance, over the last century, we have been starting to withdraw a lot of fluids from the ground, for instance, groundwater, but also oil and all that stuff. And an example is the Gulf of Mexico. Due to the withdrawal of fluids, the ground can be compressed. This leads to subsidence, meaning vertical land motion that is measured by the tide gauge. So these are the two processes, and that complicates the whole process of estimating sea level changes with tide gauges, because we have a different type of measurement. There have been in the past, there have been different types of reconstructions that have tried to tackle that issue. Traditionally, of course, people have started to just average long and complete tide gauge records around the world, simple averages. They have tried to avoid regions where we know that there are very strong tectonic signals in the data. But over the recent decades, there have been different groups trying to improve on that. Some have used a priori information about the processes, regional processes affecting sea level to correct local measurements and then estimate global mean sea level from the tide gauge records. Others have tried to reconstruct the entire geometry of sea level change. But these are just two groups. In this plot shown here, that's actually a plot from a paper that led by Thomas Frederiksen from JPL that we published last year in Nature, which looks at global mean sea level and its budget over the 20th century. And in this plot here shown are a few global mean sea level reconstructions on the left side, the total sea level, in the middle, the rates, and on the right side, the rates for linear rates for different periods from different groups shown by the different colors. And you can see that independent of the groups, all the reconstructions show that global mean sea level has been increasing by approximately 1.3 to 1.7 millimeter per year since 1900. All of these reconstructions shown here also agree on a positive acceleration over the 20th century. And most recent results suggest that this acceleration has been starting in the late 1960s. These estimates are also consistent with independent estimates of major contributions of barystatic sea level changes and thermal expansion. This is shown in the middle here by the black curve. That was the major topic in that particular paper, but that holds only for the global mean. So while we can close that budget for global mean sea level nowadays since 1900, we can't solve sea level budgets along the coast where sea level matters the most. And of these reconstructions shown here, there's no reconstruction actually providing regional fields of sea level change, local sea level change, plus the individual contributions. And that's something that I want to tackle today. And for that, I have been using a technique that has been developed by Carling-Hay and colleagues at Harvard University in 2015. It's based on an ensemble Kalman Smoother. The Kalman Smoother has several features that are very, very good for estimating sea level changes. In particular, it naturally accommodates data gaps and fills data gaps automatically based on previous states and including a priori information on the processes of sea level change. The general idea of this ensemble Kalman Smoother, without going too deep into the mathematical methods, is that we have a priori knowledge on the spatial patterns of sea level change. For instance, we know principally how Greenland or Antarctic ice melt looks in terms of sea level, the sea level response globally. I have shown these pictures at the beginning. If you remember, we have that gravitational response, and this is actually shown in these little maps in the upper right. So for instance, the Greenland, if Greenland ice melts, we will see a sea level fall near the Greenland ice sheet and a sea level increase in the far field in the tropics. So we know that pattern. And if we now look at the tide gauge records and see large differences, large gradients, for instance, along the northern European coastlines, we might interpret these gradients in sea level change in terms of ice melt. And that was the basic idea in the development of that Kalman Smoother from 2015. The initial idea was actually to estimate from the tide gauges using the spatial information of the principal processes of sea level change to estimate the budget of sea level, to estimate each individual contributor from the tide gauge record. So, but back in the days, I have to say there were no independent estimates available from Greenland ice melt and Antarctic ice melt and glaciers only very rudimentarily. So the idea for that was really using the tide gauge records and just the spatial fingerprints that are fitted to the tide gauge records. In addition, the authors used different models of glacial isostatic adjustment and ocean circulation information from climate models, from 6 climate models in that particular paper. And in this plot here on the left side, you can actually see what the Kalman Smoother really does. The black arrow bars show linear trends for 14 selected stations around the world. They are very well distributed around the world and very often used. And you see that the linear trends over the 20th century vary significantly from station to station. With the Kalman Smoother, it's now possible to interpret these spatial differences and try to fit the different processes to the tide gauge data and reconstruct the entire surface of the ocean. When doing that, with the technique from 2015, we get this red line. These are the linear trend estimates at the closest location to the individual tide gauges shown here. And you can see that this Kalman Smoother has done a reasonable job at that time in explaining the spatial variations seen in tide gauges, but it's certainly not a perfect fit. One of the reasons that it wasn't really working locally very well was the fact that the fingerprints of glacial of glacial melt or ice sheet melting have very similar spatial patterns. For instance, the Greenland fingerprint and the Iceland fingerprint are very similar. So it's very difficult to distinguish between the two sources. So that means it was impossible at that time to really reconstruct local sea level changes. It was good technique for estimating the global average, but it was not possible to separate the individual contributions. And we were still left with a lot of uncertainties on the regional scale. So that was actually the motivation why I thought to update that Kalman Smoother. And that's what I'm presenting today. Since 2015, we have got several independent estimates of barystatic sea level change, in particular the ensemble that has been published by Thomas Frederiksen et al. In the budget assessment. This provides independent estimates of ice sheet and glacier mass loss and terrestrial water storage over the entire 20th century. Plus their spatial variations. So we have that available in terms of a 100 member ensemble at every place around the world. So instead of fitting the theoretical static fingerprints to the tide gauge record, we can now replace that prior information, including the temporal information from independent estimates of ice melt, which is much more accurate. And provides and overcomes then that problem that we don't need to estimate the spatial distribution from fingerprints that are highly correlated with each other. I'm also using GIA models. Here in that assessment, I'm using 6 very state-of-the-art glacial isostatic adjustment models that are integrated into the Kalman Smoother. And I'm increasing the number of ocean circulation models that are assimilated. In particular, I'm including several ocean reanalysis models. Ocean reanalysis, other than climate models, assimilate temperature and salinity observations or sea surface temperature. So they are very close to the observational state. And that information is included, plus a few more climate models as well. The result of that update of the Kalman Smoother with that new prior information leads indeed to an improvement. So just looking at the 14 tide gauges that I showed already before, Now I added that yellow curve, which is actually the linear trend estimate from the updated Kalman Smoother. And you can see that we now do a much better job. We can now explain most of the tide gauge trends with the Kalman Smoother, meaning that the inclusion of the barystatic mass changes is indeed a very big improvement. So, but we will look into the details on the following slides. I have to mention, without going into the details, that we run the Kalman Smoother in a hybrid version, which also takes into account some spatial information from satellite altimetry. That hybrid version has been published in a paper in Nature Climate Change in 2019. So for those who are interested, can read into that. But it's very similar to the other one. There are only slight adjustments that don't really matter for the assessment here. So that's why I'm skipping that. So here are actually the first results of that new assessment in terms of regional sea level trends. Shown here at the top is the map of regional sea level changes from satellite altimetry. I have shown that map already before. On the top from CSIRO satellite altimetry. And then below we see the estimate from our new updated Kalman Smoother. And you can see that the two trend maps over 1993 to 2018 agree very well. So most of the red patches and blue patches seen in the observational map from satellite altimetry are very well reconstructed by the Kalman Smoother as well. This is reflected in a pattern correlation between the two maps of 0.6, which is statistically highly significant. We also get an updated global mean sea level curve that is shown in blue here from 1900 to 2018. In black overlaid, we see the satellite altimetry record. So we see that our reconstruction replicates the satellite record very well, both in terms of the trend as well in terms of as well as in terms of the variability. The linear trend of that global mean sea level curve is about 1.5 millimeter per year since 1900, which is in good agreement to former assessments. But the big new thing with our new approach, we are now able to not only estimate the global average, but also separate barystatic from steric sea level changes. This is now added in these plots. In blue, we see again our total global mean sea level reconstruction over 1900 to 2018. And then in black and red, the barystatic and steric contributions respectively. So we see that over that period, barystatic mass changes have dominated the budget. So they account for approximately 2/3 of the increase over the entire 20th century. Thermal expansion has been fairly constant over the first half of the 20th century, but then increased significantly since the 1960s. We can also look at the nonlinear rates of sea level change. They are shown on the right side. And you can see that the total sea level is has been fluctuating between 1 and 2 millimeters per year in the first half of the 20th century. But then at the end of the 1960s, we see that gradual increase, the acceleration in global mean sea level. If we look at the two different components, steric expansion and barystatic sea level changes, we see that the steric component actually initiated that acceleration in the 1960s. But the barystatic mass changes, primarily to the additional contributions from Greenland and Antarctica, have started to dominate the budget since the end of the 1990s. As a validation of our budget component, in particular of the steric component, I also plotted in green an estimate of steric or global mean steric sea level changes from Chen and colleagues, published in Nature Climate Change a few years ago. This is a multi-product, this is an average of multiple observational products based on Argo floats and hydrographic profiles. So it's entirely independent of our assessment, because our assessment is entirely based on tide gauge records and only takes ocean circulation information from reanalysis and climate models regionally, but the global mean is entirely based on the tide gauge record. And you see that both curves agree fairly well. Both have slightly higher rates at the beginning of the 1990s, a little dip at the beginning of the 2000s, and then an increase to more than 1 millimeter per year sea level change over the recent years again. So, as I mentioned, one of the aims was this global mean sea level budget, but the other aim was also to be able to solve that sea level budget not only in the global mean, which has already been done before with independent with a different technique, but also at the local scale. And before coming to that, I would like to give you a little background. Previously, it was impossible to do these kind of budget assessments at a local scale. And the reason for that is the stereodynamic component, or the steric height. The problem is, if we imagine that we have a tide gauge along the coast, and we have that tide gauge measurement, we also have an estimate of barystatic sea level changes and their local imprints at the tide gauge. But what is missing is the contribution of the steric height. Well, you would say that I could probably now take temperature and salinity observations from the ocean and estimate that component near or close to the tide gauge. The problem is here that the steric component is defined as the depth integral, or the density changes integrated over depth, meaning that the deep ocean has a much higher potential to produce steric sea level changes than the shallow coastal ocean. So near tide gauge, we usually at the coast, we have depths of only a few tens to 100 meters or something, meaning the potential of that water column is very small. If we would estimate the steric component directly near the tide gauge, it would be close to 0. In the open ocean, with 3,000–4,000 meters, it explains the majority of the sea level changes. What that means, in fact, is that if the deep ocean expands with the same warming as the shallow continental shelf ocean, this leads to a gradient in sea level, meaning that the added, or the sea level increase that we observe in the deep ocean needs to be transported to the coast. And that happens by different processes such as wave propagation, ocean circulation plays around. But that means that we can't use estimates of temperature and salinity changes in the deep ocean to estimate coastal sea level. We have a technique that we published earlier this year, where we try to find the source regions of these variations. That's a very first attempt using temperature and salinity data only. But today I want to show you how the Kalman Smoother overcomes that problem. So I'm not really talking about this, but the Kalman Smoother itself overcomes the issue by estimating global average steric sea level change directly from the tide gauges, in addition to the information of ocean circulation changes that we get from different ocean models. And we estimate that steric component as a weighted average of all these assimilated models, plus that global mean from the tide gauges. So the Kalman Smoother framework overcomes the issue. It integrates ocean circulation changes assimilated by climate models and ocean reanalysis on a global scale. And so we get it at every individual grid point. An example how that looks like is given here for a tide gauge in the North Sea and Northern Europe, the tide gauge of Cuxhaven along the German coast. Blue shows the tide gauge record since 1900. In gray, we see the budget as estimated by the Kalman Smoother. and then the individual contributions that are estimated for the budget. The stereodynamic component based on global steric and ocean circulation changes is shown in red, and you can see that the ups and downs seen in the tide gauge are dominated by that component. So it gives a really realistic picture. In black, we can also see the barystatic GID effects, so the spatial fingerprints, and in green, the glacial isostatic adjustment signal that are all estimated within the Kalman Smoother at the same time. So now that I have explained that that's possible, the cool thing is that with the Kalman Smoother, we now get the budget at every place around the world. And these individual budget components are shown in this plot on the bottom of the slide. In the upper part, you can see the three different budget components that we take into account in the Kalman Smoother. On the left side, the stereodynamic sea level changes. In the middle, the barystatic GID effects. And on the right side, the glacial isostatic adjustment signal. The lower map actually shows for every location around in the world's ocean, which of the three contributions has been the dominant contribution at that specific location. So blue dots correspond to the barystatic sea level change, red dots to the stereodynamic sea level change, and green dots to the GIA signals. If we look at that map, at these maps, we first see that the barystatic GID effects have been the dominant factor over the vast majority of the ocean since 1900. And GIA, for instance, is of course dominant only at those locations of former ice sheets, that is primarily Scandinavia and North America. And the stereodynamic component is dominant in some parts of the Southern Ocean and a few parts of the North Atlantic, which is also makes sense because if we look at the barystatic sea level change signal, because of the vicinity to these major melt sources, 20th century sea level change due to mass loss of glaciers and ice sheets has been relatively minor in Northern Europe and North America. So we can also go to all tide gauges that we have worldwide and compare now our full budget or the full sea level signal from the Kalman Smoother as the sum of the individual contributions of stereodynamic, barystatic, and GIA to tide gauges. And this is actually shown in the map. On the left, you see the differences between the linear trends estimated from tide gauges and the nearby solution of the Kalman Smoother. You see there are still some red and blue dots, which means that the trend is either over or underestimated. But on a global scale, we have a relatively good agreement leading to a correlation of 0.6 and a root mean square error of 1.8 millimeters per year. This is also visible if we look at the scatter plot on the right, which compares the linear trends of observed sea level change from tide gauges with the Kalman Smoother solution. So while this is already principally a good result, given that we were never able to solve the sea level budget locally over the 20th century yet, we have to keep in mind that our Kalman Smoother estimate only covers a fraction of the processes that we actually observe at tide gauges. So as I said, it contains stereodynamic changes and barystatic changes and also GIA models. But if you remember from the beginning of the talk, vertical land motion is not only induced by natural causes such as glacial isostatic adjustment, but also by processes like groundwater depletion and other anthropogenic factors that are not induced by glacial isostatic adjustment. Those have not been included in the Kalman Smoother, And indeed, if we look, for instance, in the Gulf of Mexico, where we know that we have a lot of fluid withdrawal and nonlinear vertical land motion, that is still in the tide gauge, but not included in the Kalman Smoother. So what we can do, however, nowadays we have the global the GNSS system measuring vertical land motion on a global scale at different locations and also at tide gauges. And they measure just the motion of the land. So we can use these estimates to get residual vertical land motion that also takes into account these other processes and correct the individual tide gauges around the world for these processes, and then compare again to our Kalman Smoother solution, which doesn't account for these processes. If we do that, the correlation indeed increases to 0.9, and the root mean squared error is further reduced to 1.2 millimeter per year, meaning that at a lot more locations worldwide, we are now able to solve the local sea level budget with reasonable, to a reasonable degree. So in the last part of my presentation, in the last minutes, I want to flip that topic around. Now that I have mentioned that part of the disagreement between the Kalman Smoother and the tide gauges, the local tide gauges, is related to processes that are not modeled by the Kalman Smoother, like vertical land motion. The question, of course, naturally arises whether we can actually, use the difference between a tide gauge and the Kalman Smoother to estimate vertical land motion directly. As a background for that, vertical land motion estimates that we nowadays have are only available via GNSS, which is only available since 10 to 15 years in most locations, or in most locations even less than 10 years, or by the difference between tide gauge and nearby satellite altimetry, which is also limited to the last 20 years. So our reconstruction from the Kalman Smoother now goes back to 1900, which offers the possibility to estimating vertical land motion from the difference between the two back into the early 20th century. And that's actually an ongoing project that we have within the framework of the NASA sea level change team. So initially I planned to show you actually two examples, but my animation is not working here. One example for Galveston and one for Manila. In this plot, you can see in blue the true tide gauge record. In this case, Manila. On the Philippines, you can see that sea levels have been rising there by a moderate rate until the 1960s. And then we see this steep increase of 15, 16 millimeters per year sea level change since the 1960s. And that has been previously explained by the increasing water demand from the city and the increasing population, meaning there was a lot of groundwater withdrawal. So we can estimate that, and that groundwater withdrawal, of course, leads to vertical land motion. And we can estimate that vertical land motion in the same fashion by now subtracting just the Kalman Smoother solution from the original tide gauge. And that produces this red curve, which shows a constant vertical land motion rate until the 1960s, and then the steep increase since the 1960s. And different to GNSS measurements, which are only available over the past few years, these provide nonlinear rates of vertical land motion over the entire 20th century. For comparison, I'm also showing in yellow another state-of-the-art technique to estimate vertical land motion from the difference between tide gauges and nearby satellite altimetry. And you can see that the yellow record that is overlaid on the red curve shows a very similar signal than our estimate as the difference between the tide gauge and the Kalman Smoother, meaning that we can actually interpret these differences in terms of vertical land motion. An additional point that we can detect are actually measurement errors or datum shifts that may still be in some tide gauges. I haven't prepared an example for that, but that's also an ongoing project where we look whether there might be undetected datum shifts. I did a quick global comparison to the technique of tide gauge minus satellite altimetry. This is shown by the scatter plot in the lower left, and we get a very, very good correlation between the two estimates in the order of 0.91, and the RMSE of that is a little bit above 1 millimeter per year, which is very, very precise and underpins the suitability of our technique. Yeah, that's all for today. So some take-home messages before I finish. The sparsity of the sea level observations, being it in terms of tide gauges or hydrographic data or any other contributions, hampers nowadays a proper estimation of global and regional sea level change, and in particular of the budget along the coast. And it's very important to understand the different sea level contributions along the coast where it matters most, to also properly project it into the future. We reformulated here the Kalman Smoother that has been invented by, or the technique has been introduced by Carling-Hay and colleagues in 2005. But we changed it with now with updated prior information, primarily on the barystatic mass changes, but also with new ocean reanalysis that provide information on ocean circulation changes. And this indeed allows for the first time for an improved assessment of the 20th century sea level budget, both globally and locally. The new estimate shows an agreement with former assessments, an increase in global mean sea level of 1.5 millimeter per year over 1900 to 2018. It also shows a significant acceleration that has been initiated in the 1960s by steric expansion that was primarily initiated in the Southern Ocean, and has further increased since the late 1990s by the increasing contribution of barystatic mass changes. And the latter is very important to keep in mind because ice sheets are the big tankers of sea level rise. Once they have started, they are very, very difficult to stop. They still contain an equivalent of 65 meters of sea level change. So they are a much, much bigger risk than the steric contribution. So it's a very worrying sign that we nowadays see the barystatic sea level changes, in particular due to Greenland and Antarctic mass loss, being a dominant contributor to the budget already. A comparison with nearby tide gauges allows us also for the detection of unmodeled processes such as vertical land motion or datum shifts. And this actually shows as an overall summary a statement that the use of multiple data sets, being it observations or ocean models, and bringing it all together in such a framework as in a probabilistic framework, such as the Kalman Smoother, now allows for the estimation of many, many different processes, which I think is a great improvement to the state before. So if you're interested in more details on the different techniques and the results, here's a list of a few papers that have been covered in this talk. Yeah, or just ask me now. I'm open to questions. Thank you for your attention first.
Thank you so much, Sönke. Incredible presentation. You could have saved me a lot of effort if I had heard this as we were putting together that Nash Academy proposal. It would have been a huge help. And also, I want to let people know that much of the artwork that was in backgrounds and other images in Sönke's presentation were the contribution from his wife. So incredible and really beautiful. I would like to open the floor to questions from the group, because I will be staying on afterwards to ask them specific questions. So anybody have any questions? I think there are a few in the chat that I will, the people can ask if they want. Let me just, so Alex, would you like to ask your question, or would you prefer me to read it?
Yeah, sure. It's just a basic question, like I mentioned in the chat. So when you apply ensemble smoother, I assume it's still based on the second order statistics, right? So in that case, do you need to assume like a linear Gaussian type of distribution? In data before you apply the ensemble smoother?
Yes. I want to say at the very beginning, in terms of the details of the Kalman Smoother, it has been developed by Carling Hay. So I'm more of a user of that and handling the input and outputs. But that part, I think, is in principle handled by the fact that we incorporate prior information on ocean dynamics and estimate at the same time the barystatic GID fingerprints. So that reduces that and ensures that the residual is normally distributed.
Great. And I think Patrick Heimbach has some questions.
Yeah, hi, Sönke. Really nice presentation, and also really nice artwork.
Thank you.
I have a couple, well, let's say this one question. The use of the reanalysis, you're probably aware, they are not actually property conserving, right? So they don't conserve energy, they don't conserve volume or mass. So you, most of them, not all of them, but presumably you must have done something to them to be able to use them consistently, or?
Yeah, I mean, that's sorry if I haven't made that particularly clear, but I'm actually only using the spatial pattern of sea level changes. So I'm not using the global information. Maybe for the others in the Zoom room, ocean circulation models nowadays, in most cases, only conserve volume, but not mass. So they don't simulate global sea level change, but they are able to simulate regional variations, mass redistributions. So I'm using only the spatial information, and I'm estimating the global average solely based on the tide gauge record. So it's really just to explain the difference between, let's say, Newland and New York or something.
Okay, yeah, and in fact, it's more than that, right? Not just the ocean models being volume conserving, but also the reanalysis actually not conserving anything, sequential reanalysis.
Yes.
So, yeah, great. I have more questions, but maybe I should leave the floor to others. So
Thank you.
I don't see anything else in the chat. Patrick, if you want to ask one or two other questions, go ahead.
Okay, well, sure. I'm curious, you showed very nicely at the beginning with the removed global mean trend, you see over the altimetric record, the regional variation in sea level trends. And over it's sort of a multi-decadal pattern, right? So 20, 30, well, by now almost 30 years. And so there's a lot of talk about, multi-decadal, decadal to multi-decadal sea level predictions. There seems to me that, I think there's an agreement that a lot of it is internal variability on those timescales in the climate system, which makes that, would you agree that that makes that very hard to do on these sort of, let's say, tri-decadal timescales, or is there a hope that this could be done?
Yes, maybe step by step, I fully agree with the statement. Internal variability is a very, very important factor. And if we just look, for instance, at the global average curve that we got, we nowadays have estimates that the satellite record, the global average, shows an acceleration, right? And many have claimed that this is a significant acceleration, which is maybe truth if we really just look at these nearly 30 years that we have with a common noise model. But if we look at the history of sea level change, we probably know that similar accelerations have very likely occurred before. So it's, from a statistical standpoint, not significant, although we know what is really happening. And this is actually visible when we look at this and at these nonlinear rates. The rates that we have observed over the last few years, over the satellite period, have been with a similar amplitude already happened in the 1930s and 1940s. So I personally wouldn't claim that the acceleration is statistically significant from that standpoint, but we see that this acceleration that we have obtained over the satellite record, that it has already been initiated in the 1960s. So the persistence is indeed very, very strong. So that's one of the things. In terms of the regional variability, I fully agree. It becomes even more difficult because we have much more processes that contribute to that. With this kind of reconstruction that we have, I'm hopeful that at some point we can do a more proper statistical assessment whether the spatial patterns over the satellite record are significantly different to former periods or not. So I'm still skeptical, but open to be convinced by others who are doing that kind of work.
Thanks. Yeah, I agree.
Does anybody else have any questions? So I think maybe we can thank Sönke, and I'm sure we will have, Michael, go ahead.
No, that was a clap.
Oh, sorry.
Excellent talk, Sönke. Thank you.
Thank you very much. Appreciate it.
And
thank you for the invitation.
And I think we will certainly have you visit when you come further south, and looking forward to collaborating hopefully with you and others in Louisiana in the future. So if you stay online,
thank you. I appreciate
you and I and Ashraf can talk a little bit, and then others can log off if they